Yes. So good evening all. Welcome to your new session in mass spectrometry. So initially in mass spectrometry, especially with respect to 3 videos, we discussed about what is introduction, application and what is general principle involved in mass spectrometry. Later on we learn how to generate molecular ion by ejecting one of the electron by applying 7 to 15 electron volts. So then later on we learn what is a molecular ion, how molecular ion is going to be identified, and what are the recognition techniques of molecular ion. Okay, and even we also learn about what is stability factors involved in molecular ion formation. Okay, so generally in mass spectrometry, last peak is most probably belongs to molecular ion peak, but that is not mandatory. Maybe last peak may be a impurity peak, last peak may be a isotopic peak, may be molecular ion interaction peak. So variable possibilities are expected in case of last peak. So later on we learn about how recognition is possible with respect to variable lighter isotopes and heavier isotopes by substituting in that one. Okay, so next, after recognition of molecular ion, next concept is fissions. Now we are going to discuss fissions which are going to be helpful in fragmentation. Okay, so types of bond fissions. Types of bond fissions in mass spectrometry. So this fissions applicable even for your GOC also, but most probably these fissions are most helpful in mass spectra. Okay, so generally bond fissions in mass spectrometry, they are classified into 3 types. Bond fissions are classified into 3 types in mass spectrometry. So first one is homolytic fission. Second one is heterolytic fission. Then hemi-heterolysis. Third one is hemi-heterolysis. 3 types of bond fissions are commonly observed. So bond fissions are classified into 3 types. Homolytic fission in mass spectrometry, then heterolytic fission, one more is hemi-heterolysis. This is also called semi-heterolysis. Homo, hetero, and it is a mixture of these two. So that's why it is called hemi-heterolysis. So first we are going to discuss homolytic fission. Homolysis, also called homolytic fission. So these fissions are most helpful. If you want to write any fragmentation mode clearly, this is very, very important one. Okay, what is homolytic fission? Generally we can define like this: symmetric cleavage of covalent bond. Covalent bond I am cleaving symmetrically. That is called homolytic fission. I am breaking equally, nothing but homolytic fission. Otherwise you can say symmetric cleavage of covalent bond is called homolytic fission. Okay, how it is represented? It is represented by Fishhook arrow symbol. Fishhook arrow symbol is generally used for this one. So this is a symbol used for homolytic fission. So after generation of molecular ion, we can use homolytic fissions. Remember, so cleaving equally, breaking exactly from middle of the bond. If you break any covalent bond exactly middle of the bond, 2 atoms will take their own electrons and make them into radical formation. So most commonly homolytic fission leads to formation of a radicals. One more time it will comes in GOC. Right now I will give an example. See, A and A I am using now. Suppose if I use either photochemical or thermal, normally I am saying here 2 electrons are present. This 2 electron belongs to A and A. Homolytic fission, this is left side and this is right side. Then what happens? A radical and one more is this A radical will be formed here. Homolytic fission. Suppose if I take chlorine and chlorine, same. Photochemical thermal, here 2 electrons are present. You may use any one. There is a formation of how many chlorine radicals? 2 chlorine radicals. So means from where I am breaking now? I am breaking exactly from middle of the bond. So during this particular breakage, 2 electrons, initially they are belongs to this one and this one. After breaking, this electron belongs to this one, this electron belongs to this one. So finally we are breaking equally. Suppose if 2 electrons are present, 1 1, 4 electrons are present, 2 2, 6 electrons are present, 3 3. That is called homolytic. It is also called homolysis. Clear? Right. Symmetric cleavage of covalent bond is called homolytic fission. It is represented by Fisch's arrow symbol. So homolytic fission leads to free radical. What is this? Free radical, independent electron. Free radical formation takes place here during homolytic fission. Okay, so this you observe clearly. This is CH2, carbon-carbon double bond. I am writing. Is it a allyl carbon or not? Allyl. Suppose if I apply 70 electron volts, initially forms molecular ion or not? What is molecular ion here? This is CH2 hydrogen. Can I remove electron from pi bond or sigma bond? Pi bond. So if I remove electron, now one of the pi electron is going to be removed here. Here how many electrons are present? 2. Remove one of the electron. If I remove here, you will get radical, and what is this? Positive charge. Is it right? See, molecule having sigma and pi electron, during electronic impact, one electron is removed and you will get a radical cation. Is it a molecular ion? This is molecular ion. What about this? This is molecule. So now what I am doing is I am doing homolysis. Homolysis over here. See, this carbon hydrogen bond I am breaking here. If I break here, hydrogen become radical, carbon become radical. Right? Hydrogen is removed in terms of H dot. What about carbon? Carbon is removed in terms of radical or not? Here radical. And already one radical is present on this carbon or not? This carbon having radical. This carbon also having radical. Radical, radical, there is a formation of double bond. And what about this carbon? Positive charge. That's it. After formation of molecular ion, these fissions are applicable. Be prepared. After formation of molecular ion, apply homolytic fission, heterolytic fission, hemi-heterolysis. So don't apply initially. If you apply initially, that is also possible, but that is not included in mass spectrometry. If you want to apply these fissions in mass spectrometry, remember we are applying these fissions after generation of a molecular ion. See, first I used electronic impact by using 7 to 15 electron volts. So one of the electron is removed and I got a radical cation. This radical makes a rupture and break this bond. So this electron taken by hydrogen, this electron combine together and forms double bond by leaving this cation and this carbon. You will get allyl cation. Final answer. Clear? So what type of fission observed between carbon and hydrogen? Homolytic fission. Is it clear? One more example I will show. Just listen. See, this is benzene. 70 electron volts I am applying. So where should I remove electron? From pi electron or not? Remove one of the pi electron. If I remove one of the pi electron, then see, this is radical and this is cation, right? So now see, here this hydrogen I am removing now. This is homolysis and break this bond. If I break here, this radical both are present. This radical combined with this one and forms double bond or not? This radical forms double bond. But this carbon carry already positive charge. And what about hydrogen? Removed in terms of radical. Then what is this? Phenyl cation. So what is MZ value of this one? Here MZ value of benzene is how much? 78 or not? This is 78. I removed one hydrogen. Then it becomes MZ value is 77. This you remember. If I remove one hydrogen, it becomes a phenyl cation. It is a radical cation. It is benzene. Benzene radical. Benzene radical carries 6 pi electron delocalization. MZ value is 77 and this is 78. Now it is a homolytic fission. Clear? Right. Every time try to generate molecular ion first, then apply the fission. Okay, so I am taking a toluene. If I apply 70 electron volts, where you will remove electron? That's why first I explain how to remove electron to generate molecular ion. Where should I remove electron? From pi electron or sigma? Pi. Can I remove one of the electron here? If I remove one of the electron, you will get radical, and what is this? Cation. And what about this? CH2 and here hydrogen. Can I write? CH3 I am going to represent in a 3 different forms. Okay. Now this particular bond I am going for homolysis. Homolysis or homolytic fission. Now see, this bond I am breaking. Initially hydrogen having one electron, carbon also having one electron. This electron forms. What is your answer? Now these two will form a double bond. Here if this radical combined with this radical, then here carbocation is left or not? And what is removed here? What is removed? Hydrogen is removed in the form of hydrogen radical. So what is implicit value of this one? See, implicit value of this one. So this is 91. Implicit value is 91. How many carbons are present? 7 carbons are there. 7 into 12. 84. 84 and this is 2 hydrogens. 84 plus 2. 86. 87, 88, 89, 90 and here one hydrogen is left. Here hydrogen is there or not? 91. Initially what about this one? Is it a radical cation or not? Implicit value it is 92. Tropylium, you remember. This is called tropylium. So if this bond will migrate here like this, after 91, if I write one of the resonating structure, this is a resonance symbol. Now I can write that positive charge outside. If I write like this molecule is called implicit value 91. What is this? Benzyl cation. What is this? Benzyl. Even for tropylium, tropylium also will get 91. Tropylium will obtain from this molecule only. Okay, so this molecule on getting rupturing, you will get tropylium. I will explain later, but right now remember, after getting this one, if this double bond migrate inside, you will get 91. Both are same. Every time generate molecular ion and keep on showing a proper fission. So every time what I am showing now? Only homolytic fission. Means I am breaking symmetrically or not? I am not giving any priority towards carbon side and hydrogen side. Equally I am breaking. That's why it is called homolytic fission. Suppose one more I am giving now. This is chlorine. Here 3 lone pairs are present. 70 electron volts. So what do you expect here? Can I get chlorine with radical cation? Right? Now, from here to here, what is this? Loss of electron. Is it a molecular ion formation? Now, I want to do homolytic fission. See this. This carbon hydrogen I want to break. You can break carbon-carbon bond as well as carbon-hydrogen bond. See, carbon having one electron, hydrogen also having one electron, break this bond. Homolytical. This radical forms. What do you expect? Double bond or not? Here CH, carbon, chlorine double bond, and here plus, here lone pair, hydrogen is removed in terms of H dot, over, common. So what is the kind of fission here? Homolytic fission. Okay, every time remember, after generation of molecular ion, fissions are applicable. First what I explained, how to generate molecular ion. What is the order of removing electron? Non-bonding, pi electron and sigma electron. That order explained already. Okay, one more example I will show. Try to identify this. See, I am giving alcohol. Here 2 lone pair of electrons are present. If I apply 70 electron volts, where should I remove electron? From oxygen or not? If I remove electron from oxygen, what is your answer? You will get radical cation, right? Now, after this, what happens? Molecular ion formation takes place. Similar to halogens, can I remove this? Similar to this process. If I break homolytic fission between carbon and hydrogen, this radical combine together and forms here CH, carbon oxygen double bond, hydrogen is left, and here one lone pair is left, and what is removed here? Hydrogen. Is it right? Any new thing we learn? No. First, slowly we are learning how to make fragmentation. Up to now we learn how to generate molecular ion. What are the possibilities of generating molecular ion with respect to different electrons? Then stability of molecular ion. Then recognition of molecular ion. At last, slowly we are entering into fragmentation. So next is fragmentation only. So if you want to write any fragmentation, you should know how to break. How to break, whether we are transferring 2 electron, 1 electron or radical cation. Clear? So will you apply this? Similar for any amine. This is amine. 70 electron volt. Where should I remove electron? From nitrogen or not? If I remove electron from nitrogen, you will get NH2 and this is radical cation. Right? Here carbon nitrogen bond is there. If I break this one, will you get same answer? Right or not? This radical combine together and forms double bond. CH3 carbon nitrogen double bond, NH2 and this is plus, there is a loss of hydrogen radical. Same pattern or not? So if you know one point clearly, you can recognize all fragmentations clearly. Only thing is whether it is homolytic fission or heterolytic fission. If you know clearly, answer is over. Try to apply the logics every time. First you take a neutral molecule, eject one electron from their gaseous state and forms a radical cation, becomes a molecular ion. From molecular ion, homolytic fission, here also homolytic fission, homolysis. You need to identify whether we are doing homolytic or heterolytic. So next one, heterolytic fission. Second one is heterolytic fission. Heterolytic fission. So this is almost all same, but 2 electrons we are transferring. Unsymmetric cleavage of covalent bond. Unsymmetric cleavage of covalent bond. Transfer of 2 electron. Here we are going to get transfer of 2 electron. Transfer of 2 electron or high electronegative atom. So between 2 atoms, if any covalent bond is present, One should be high electronegative, other is less electronegative. If you transfer the 2 electrons to high electronegative element, that is called heterolytic fission. So in homolytic fission, how many electrons are present? 2 electrons. But we are breaking equally. Means 1 electron. But here we are transferring 2 electrons to one atom. Okay, we are not breaking equally. We are breaking unequally. So unsymmetric cleavage of polar covalent bond is nothing but heterolytic fission. It is not a normal covalent bond. It should be polar covalent bond. So transfer of 2 electrons on high electronegative atom leads to cations or ions. So it is represented by fully headed arrow. It is represented by fully headed arrow symbol. Fully headed arrow symbol is represented between two. So means we are transferring 2 electrons on one high electronegative element. Suppose A and B I am using heterolytic fission. See here 1 electron is there, B also having 1 more electron. Initially this A having 1 electron, B also having 1 electron. During heterolysis this electron transferred to B. Mostly right side high electronegative elements are present. Now A carry positive charge. What about B? B carry negative charge. B taking one additional electron from A. B having its own electron. It is also taking A electron. That's why -1 indicates 2 electrons. Its own electron and extra electron becomes -1. Now A is losing its own electron. That's why A plus. That's why unsymmetric cleavage. It is not symmetric cleavage. We are not breaking exactly from middle. Unequally we are breaking. So transfer of 2 electrons on high electronegative element or atom. So during this definitely that bond should be polar. So we can write polar covalent bond. It should be polar covalent bond. Transfer of 2 electrons on high electronegative atom. So definitely it should not be same. See, these 2 elements should not be same. Suppose if chlorine not possible. Possible, but medium should be changes. Here we need to change the medium, acidic medium, basic medium. On that time it is possible. But normal if you apply, so without medium if you want to do heterolytic fission, on that time these two should be differ. Hydrogen chlorine, hydrogen bromine. Okay, here high electronegative element and here less electronegative element. Mostly acids. Okay, most of the acids they will release proton. That proton is nothing but H plus. And what about this? It is a negative ion. It is a conjugate base. Clear? Suppose if you apply this CH3CH2 here Cl. Now I am generating molecular ion. What do you expect? Here chlorine radical cation like this or not? Now then apply heterolysis. This is heterolysis. Here carbon having 1 electron, chlorine also having 1 more electron. Now this electron added on this side. This radical as it is, but this electron added to this empty cavity. Already during electronic impact 1 electron is removed or not? There I am adding this sigma electron. So here what will you expect? Chlorine carry 3 lone pairs or not? This electron I am adding here. Then this radical will be as usual. Then what about this side? This side you will get a carbocation CH3 CH2 plus. That's it. Clear? That is the meaning of heterolysis. So mostly alcohols, halogen derivatives will follow this kind of fissions. Mostly for halogens it is applicable. Suppose see if I take chlorine, same. Chlorobenzene 70 electron volts. If I remove one of the electron from chlorine, then chlorine carry radical cation, 2 lone pairs. Okay. Now go for heterolysis. Then what you'll expect? See here how many electrons are present between chlorine and carbon? 2 electrons. Transfer this electron to chlorine. If this electron added here, chlorine become lone pair, lone pair, lone pair and 1 electron. And what about benzene? Benzene is removed in terms of cation. So what is MZ value of this one? MZ value is 77. Benzene is 78. One hydrogen is not there or not? See, if hydrogen is there, 78. If hydrogen is not there here, 77. Is it heterolytic fission or homolytic fission here? After generating molecular ion, 2 lone pairs and 1 radical cation is present. Now during heterolysis, this electron is added on here. This electron added here, then becomes a lone pair or not? This is added electron. This electron is this one. Here empty cavity is there because during electronic impact, 1 electron is removed. Here 1 electron is removed or not? This electron is removed and forms a molecular ion. This molecular ion, this electron I am adding here, and finally you will get chlorine radical and phenyl cation. Okay. Then third one, it is very simple. Hemi-heterolysis. Hemi-heterolysis. It is almost all equal to heterolysis only, but initially start with a homolytic fission. So generally these fissions are appeared on radical cations. On radical cation shared by sigma bond, this kind of fissions are appeared. So means indirectly I am breaking a bond having only 1 electron. Okay, radical cation nothing but having 1 electron, 2 atoms are present with positive charge. So there we are targeting. So these fissions most commonly appeared or observed only at a sigma bond shared by only 1 electrons and 2 atoms. Okay, that is called hemi-heterolysis. Okay, this hemi-heterolysis leads to formation of a radical and cation. What about homolysis? Homolysis leads to radical. Heterolysis leads to cation anion. Hemi-heterolysis leads to cation and radical. So it is exactly middle of homolysis and heterolysis. Most commonly this is possible only at a sigma bond having only 1 electron. It is also looks like a homolytic fission only, represented by Fish-Hook arrow mark symbol. But here we are using the word heterolysis because we are getting a cation here. Clear? Right. So here cleavage of radical cation. Cleavage of radical cation is called hemi-heterolysis. Cleavage of radical cation is called hemi-heterolysis. Okay, so almost all it is similar to homolysis. And especially this is leads to what you'll expect? Formation of cation and radical. This fission leads to cation and radical. Hemielectrolysis most commonly leads to formation of cation and radical. Looks like homolysis, and it is also even represented by Fishhook arrow symbol. These points you remember, Fishhook arrow symbol. Similar to homolytic fission only. Cleavage of radical cation, similar to homolytic fission, leads to formation of a cation and radical, and this fission generally represented by Fishhook, similar to homolytic as it is. But in homolytic, after generating molecular ion, adjacent we are breaking in homolysis. After generating radical cation, adjacent we are breaking, but here we are not breaking adjacent, exactly on radical cation. Wherever radical cation is formed, there we are breaking. Clear? So you will understand while taking one example. Cleavage of radical cation, similar to homolytic, leads to formation of cation and radical, represented by Fishhook symbol. Suppose if I take methane, how many sigma bonds are present? 4 sigma bonds are present, right? So here there is a formation of a radical and cation. Okay, so this is cation and here radical, right? Can I write like this? I can remove one of the electron from any one of these bond. Now what is hemielectrolysis? This is called hemielectrolysis. Here if I break, this is called hemielectrolysis, like this. Here how many bonds are present between carbon and hydrogen? Only one bond or not? This bond carry how many electrons? Only one electron. Whichever side electron is present, that side you need to transfer. See, this hydrogen carry radical, carbon carry positive charge. So if hydrogen is removed in the form of H dot, then what about carbon? If hydrogen is removed in terms of H dot, then carbon is removed in terms of CS3 plus. That is hemielectrolysis. Means exactly where we are breaking? At radical cation. Is it radical cation or not? Radical cation. Here only we are breaking and we are getting radical and cation. That is hemielectrolysis. Cleavage of radical cation. Cleavage of radical cation leads to formation of radical and cation. Leads to formation of radical and cation. Represented by which symbol? Fishhook. And it is similar to homolytic fission. Now I am giving ethane. If I apply 70 electron volts, generate molecular ion. Ethane. Where you will generate? Here how many types of sigma bonds are present? 2 different types are not. Carbon, 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 nitrogen. So where you will generate molecular ion? By removing electron between 2 carbons. If I remove electron between 2 carbons, then what happens? If one side cation, other side radical. This side is as it is, like this only. Is it right? Between 2 carbons, 1 electron is removed. You will get radical cation. Okay? Then go for hemielectrolysis. It is also called semielectrolysis. Then see, this bond is broken this side. Only one side you need to write the arrow. If I break right side, now right side is gaining 1 electron, that is radical. Plus, what about left side? Left side is gaining positive charge, radical cation. Means exactly where we are breaking? At radical cation. That is called hemi. If I use the word hemi, remember we are breaking at radical cation. Suppose if I take propane or any higher alkanes, this is CH3, CH3. If I apply 70 electron volts, so then where you will generate molecular ion? Terminal or not? You need to recollect that points. A terminal. If I remove one of the electron from terminal, here what you will get? Cation. And this is radical or not? Right? Here two electrons are present. I would like to remove from terminal. If I remove this electron, I will get positive charge here. Then after this, I want to make hemielectrolysis. Then what is your answer? Can I break this side? So what will you expect here? CH3, what is this? CH2 plus. And what about here? CH3 radical. Now remember, see, this one, try to identify the fission. If I do like this, what is this fission? Heterolysis. It is called heterolytic fission. Heterolysis. If I do heterolysis, what about CH3? CH3 cation. What about CH2? CH2 is a carbon. Like this. First molecule, neutral molecule, molecular ion, hemielectrolysis, then heterolysis. Like that, successive fragmentation takes place. Clear? So based on the arrow, you need to identify what type of fission it is. Here, what type of fission? Where I am breaking? At radical cation. So now it is hemielectrolysis. After getting cation, if any possibility is there to transfer two electrons to cation, then cation disappears their charges and forms a carbene. Then followed by carbocation. Clear? So, if I take any molecular ions also shows multi-center fragmentation. Multi-center fragmentation. So molecules also shows multi-center fragmentation. Not only homolysis, only heterolysis, not possible. Sometimes two at a time. Okay. Molecular ions also shows multi-center fragmentation. Just listen. See, this is CH3, CH, and here I am writing CH2X. What is X indicates? Halogen or not. So this carbon I am writing hydrogen. Remember. See, if I remove this bond, if I write like this, what is this fission? Heterolysis. And if I write this fission, what is this? Homolytic fission. Now what is the charge expected here? Will you expect positive charge on this carbon? And what about X here? X radical. And what about this carbon? Radical. So this carbon I can write in the form of CH2 radical, and what about this? CH2 cation. This is radical and this is cation. So can I write radical cation? This is radical and this is cation. This X is removed in terms of X dot. That X dot combined with H dot. when X dot combine with H dot and forms a HX. Now this is called dihydro. In this what I removed here? In this what I removed? Halogen I removed, hydrogen also I removed. At a time I removed or not? At a time I removed. So I can apply at a time heterolysis and homolysis. By following some general rules, some molecules will give this kind, not each and every molecule. Based on the molecule, based on the structure, some molecule will give multi-center fragmentation at a time. So this is called dehydrohalogenation. Means if any molecule have a tendency to remove a neutral fragment. So some rules are there, even electron rule, odd electron rule, there I will explain. Right now if I explain rule you will confuse. Right now see, this is a halogen and this is hydrogen. Halogen can be removed in terms of HX. If I remove hydrogen and halogen in the form of HX, this is called dehydrohalogenation. Dehydrohalogenation leads to formation of olefin. See, if I want to write a clear structure of this one, can I put double bond here? Can I put double bond between this carbon, right or not? If I write double bond, then how can I write? I can write like this or not? So when you will get double bond, when you remove some elements. So what are the elements I removed in this one? Hydrogen, halogen I removed. So removing hydrogen, halogen is called dehydrohalogenation. So dehydrohalogenation is a multi-center fragmentation. Clear? So it is a multi-center fragmentation. So this is radical and this is cation. Only 3 fissions are there. Remember, only 3 fissions are there. But the 3 fissions may be applicable individually, may be applicable at a time. One molecule, more than one homolysis possible. One molecule, more than one time homolysis. More than one time heterolysis possible. Don't think that only one time homolysis, only one time heterolysis possible. See, from here to here, how many times heterolysis I done? Only one time. From here to here, how many times heterolysis? One time. But see, this is, see, heterolysis, homolysis takes place at a time. At a time. I removed halogen and hydrogen at a time. Means here heterolysis, here homolysis. This is called multi-center fragmentation. It is not back-to-back steps. This is called back-to-back. First is what? Molecular ion formation, hemi-heterolysis, then heterolysis, back-to-back. But here it is simultaneous. At a time, both will take place at a time. That is called multi-center. Multi-center, nothing but one molecule at a time fragmentation takes place. So remember, whenever if I use the word dehydrohalogenation, dehalogenation, dehydration, they are called elimination reactions. If it is eliminated out, you will get one double bond here. That is called elimination reactions. Mostly halogens, alcohols, ethers, and even alcohols shows this kind of reactions. D, whenever if I use the word D, which indicates it is elimination, elimination leads to forms double bond or multiple bonds. So dehydrohalogenation dehalogenation, and what is one more? Dehydration. What is the meaning of dehydration? Loss of water. Dehydrohalogenation, dehydration, dehalogenation follows multi-center fragmentation. If any molecule have a tendency to remove water molecule, halogens, and hydrogen and halogen, on the time it is a multi-center fragmentation. What is the meaning of multi-center? See, this is one center to break. It is one more center to break. How many centers I am breaking? 2 centers or 1 center? 2 centers. 2 centers I am breaking at a time. Is it step-by-step process? No. See, in last case, only this bond I am breaking. Next, this bond I am breaking. So initially in this molecule, I am breaking this bond and this bond or not? In this molecule, I am breaking this bond as well as this bond, right? If I break this bond, you will get this one. And if I break this one, you will get this one. But my question is, this bond and this bond, whether I am breaking at a time? No. Step-by-step process. That is not multi-center. Multi-center nothing but breaking more than one bonds at a time. I am breaking this bond and this bond. At a time I am breaking. That at a time breaking may be 2 homolysis, 2 heterolysis, homolysis, heterolysis, semi-heterolysis also possible. Clear? Not only successive fragmentation. This is called successive fragmentation, only one fragmentation. Okay, multi-center fragmentation also possible. Suppose, see, I want to remove 2 halogens. See, here I am giving bromine and here also bromine. Suppose if I use 70 electron volts. So can I remove one of the electron from bromine? If I remove one of the electron from this bromine, this is radical cation, right? How many electrons can I remove? Only one or not? You can remove that electron from this bromine or this bromine. Any one. Now after this what happens? See, this I am removing heterolysis. Then what is the charge you will get here? Positive. Now this I am breaking homolysis. Then what about this? This is radical. This one? Bromine. See, here I am breaking heterolysis or not? X become radical or cation? X become radical or not? Then what about this bromine? Radical. Bromine radical, bromine radical. Further forms Br2. There is a formation of Br2. Then these 2 carbons are removed in terms of, this is CH2, CH2, and here this is what? Radical. And what about this? Cation. So what I removed from this molecule? Br2. Br2 is nothing but halogen or not? So I can say dehalogenation. I removed hydrogen and halogen. Dehydrohalogenation. If I remove 2 halogens, dehalogenation. Then see, is it neutral or positive? Neutral. Is it neutral or positive? Neutral. Then what is this? Radical cation or not? It is a radical cation. So remember, it is a radical cation. And what is this? Neutral. Then what is this? Is it radical cation? Molecular ion is a radical cation or not? See, radical cation. Is it radical cation? It is radical cation. When any radical cation is present, you apply this technique. This I will explain in types of ions. If any radical cation is present, that may lose one neutral and forms one more radical cation. And see, here also what is this? A neutral. And what is this? Radical cation. And what is this? Radical cation. If any radical cation is present, that always remove one neutral and radical cation. This is one rule. This point you remember. If you take any radical cation, that radical cation give a fragment such a way that it will remove one neutral and it will give one more additional radical cation, a new radical cation. This fragmentation is acceptable anywhere. This is called radial cation rule. Clear? Rc nothing but radical cation. Is it odd electron or even electron? This one. Odd or not? Odd electron. This one? Odd electron. This one? Even electron. Any radical is there here? No. Now it is even electron. When odd electron fragments, you will get one odd electron and even. But when you take even electron always give even only. That is called odd electron role. I will explain later. Right now remember only radical cation. When radical cation undergo fragmentation, that will give a new radical cation by removing one neutral molecule. One neutral molecule is going to be removed. Now, can you apply dehydration? See, this is radical cation. This is CH2OH. Here radical cation lone pair. Here CH2 is present. CH2 hydrogen. Now see, I am taking a alcohol. This is alcohol. By applying 70 electron volts, will get radical cation. This is CH2OH. This is radical cation and here lone pair and here one hydrogen. Now it is a multi-center fragmentation. What is it? Remove this hydroxy, remove this one. Then this is removed in terms of this radical as is, this radical added here. This radical and hydrogen radical combined together and forms what they will form? Water molecule. And what about this one? These two carbons removed in terms of radical cation. Still, water is removed or not? Water is neutral or any charged one? Water is neutral. Then what about this one? Radical cation. Neutral radical cation. Every time dehydrohalogenation, dehydration follows which rule? Odd electron rule. Wherever I write radical cation, if I write radical cation means how many electrons are unpaired here? One electron is unpaired. This is called odd electron. When odd electron undergo fragmentation, that will give definitely one more odd electron. And what is this? Even electron. And here also same. See, it is an odd electron. And what is this? Odd electron, even electron. This is, what is this? Odd electron. Odd electron undergo fragmentation, responsible to give. Is it odd electron or not? Then see, there is a formation of CH2 radical and cation, and what is removed? Water. Water is a even electron. Even electron nothing but neutral. What is the meaning of even electron? Even electron which carry even number of electron. Methane carry even number of electron. HX carry even number of electron. HCl, HBr, water molecule, NeX2, chlorine, bromine, all carry even electron. If any molecule, if you remove from organic site, bearing without charge, that become even electron molecule. This is even electron. What is this? It is a radical cation. Odd electron or not? This is radical cation, odd electron. Remember, when odd electron undergo fragmentation, definitely will give odd electron only. And one even electron. But when even electron undergo fragmentation, they never give odd electron. This rule you remember, that is called odd electron rule. Something you understood, I think so. Slowly we are entering into core knowledge in mass spectrometry. If you know rules, no need to learn functional groups. Directly you can attempt the examples and you can work out. Two rules remember, even electron rule, odd electron rule. Right now I given only one example for odd electron rule. What is odd electron rule is saying? What is the meaning of odd electron rule? When any odd electron participates in fragmentation, they may give, after fragmentation they may give one odd electron and one even electron. Otherwise you remember, odd electron plus neutral. Odd to odd. Odd to odd, then followed by odd to even possible. But even electron never give odd electron. Even will give even only. Every time even electron. Remember, a odd electron can give odd and even. But even electron never give even and odd. Even electron always give
Even only. That's why separate rule is there as even electron rule. Which is better? Odd electron rule is better. Why odd is better? Radicals are removing out. That radical undergo further fragmentation. One is stable, other is unstable. They undergo further fragmentation. But in case of even electron rule, both are stable. Both even electrons are stable. What is dehydrohalogenation? Loss of hydrogen and halogen. Dehalogenation? Loss of two halogens in the form of X2. What is dehydration? Loss of water. So these all are neutral molecules or not? Neutral, neutral, neutral. Here I removed one neutral. Here I removed one neutral. Here also removed one neutral. Everywhere if I remove neutral, that becomes a even electron. Even electron species. It is not ion. Now this is a odd electron ion. Odd electron ion nothing but ion carry odd number of electrons. Clear? Try to understand. So this rule I will explain later, but you identify the common similarity which is observed between these three. The technique you need to identify. So don't think that fragmentation means whatever direction they may take. It is not going to take randomly. Generally in mass spectrometry, you people, you don't know which direction fragmentation is going on. You people will think that it is a random fragmentation. Random means whichever direction they want, they are breaking. They never take like that. Remember, they are not breaking whatever direction they want. They are following one rule. That is called even electron rule. One more is odd electron rule. That will come in ions. There I will explain directly. So this is one more. So this is cyclo. What is this? Cyclohexane. So where should I remove electron? From pi or not? So if I remove one electron here, you will get radical and cation or not? Now observe clearly. Here I am giving one fission. Is it homolytic or heterolytic? Homolytic. Here also I am breaking one more. Homolytic or heterolytic? Homolytic. Is it multicenter? Yes. If I break here, here what you will get? Radical. Here, radical. Radical, radical, what you will get? Double bond or not? Plus. This radical, this radical. This radical, double bond. And what is present here? Radical. And what is this? Cation. This is radical, cation. What is this? Diene, dienophile. Diene, dienophile. What is this? Adductor. Retro-Diels order reaction. Reverse we are learning. Retro-Diels order. Pericyclic you know? Diene combined with dienophile under thermally forms a adduct. Now reverse we are learning. If this molecule undergo multi-center fragmentation, you will get radical cation and neutral. Is it neutral? Now what is this? It is a radical cation or not? Radical cation is a odd electron. And what is this? It is a odd electron. And what is this? Neutral. It is a radical cation or not? Whether we are following same rule? Yes. Reverse is what? This reaction also called retro Diels order. Retro Diels order. This is called Diels order. Reverse is retro Diels order. Now how many fissions are taking place now? 2 fissions. 2 fissions nothing but multi-center. Clear? So one more example in the form of cycloalkane. See, this is cycloalkane. If I apply 70 electron volts, there is a formation of radical and here cation, right? Where I am breaking now? I am breaking between 2 carbons, right? So here I am making one fission. This is one fission, here one more fission. What is this? 2 homolytic or not? So this radical you will get double bond. This radical combine together and forms a bond. Now here one radical, and what is this? This radical has this, cation has this. So can I write radical cation one more time? If I break these 2, here you will get double bond. This radical forms a 4-member ring. This radical cation has this. Is it a radical cation? Radical cation, neutral, and what is this? Radical cation. Possible? Is it fragmentation possible? Yes. You came to know whether fragmentation possible or not by following these rules. Every time when radical cation is given, try to remove one neutral. Not only one neutral, more than one neutral also possible. See how many neutrals I am removing. Only one neutral. Not only one neutral, more than one neutral also possible. You can remove more than one neutral and we will get one radical. That is radical cation. Clear? This is one famous reaction, see. This is alpha, beta, gamma. Later you write down, first you see this. See this. Here lone pair of electrons, sigma electron, pi, all are present or not? So from where should I remove electron? Non-bonding. If I remove electron from non-bonding, what you will get? Radical cation. Okay. Now what is this? Alpha. What is this? Beta. And what is this? Gamma. Gamma carbon or not? What is this carbon? Alpha. It is also alpha. Beta, gamma. So this gamma hydrogen I am breaking. See this. This carbon hydrogen is called gamma hydrogen. Homolytic or heterolytic? Homolytic. Equally I am breaking. Here also equally. Homolytic. Here also homolytic. How many homolytic fissions I am doing? 3. At a time 3. Now question is, sir, How can you came to know 3, 4, 5, 6 possible or not? Follow the rule. Same rule is same. You may get one radical cation, you may get more than one neutral or one neutral. Okay? See, if I break this pi bond, you will get one radical and here radical, right? And if I break here, radical, radical. And if I break between these two, radical, radical. Right? Now observe clearly. If I add this hydrogen from here to here, so can I put double bond here? This radical double bond, this radical combined with hydrogen. So you will get hydrogen, radical cation, lone pair, right? Then this radical forms. Double bond or not? Right or not? What is this? Radical cation or not? Radical cation. What is this? Radical cation. And this is a even electron. This is called McLaughlin rearrangement. Norris 2. Now question is whether this fragmentation possible or not. Yes. On which basis it is possible? On which basis? It is following odd electron rule. What is odd electron rule is saying? If any molecule have a tendency to form odd electron, during electronic impact, there is a possibility of forming a neutral and odd electron. Is it neutral or not? Yes, neutral, and this is odd electron. Possible. This reaction is possible. This is called McLaughlin rearrangement. I will give that name. So this is retro Diels order and this is called McLaughlin rearrangement, also called Norris 2. But in Norris 2, we are applying photochemical. Whether we are using any photochemical here? No. This is not Norris 2. But actually see, here if I use light symbol, photochemical symbol, that is called Norris 2. But I am not using light here. Whether I am using electromagnetic radiation? No. What I am using? A beam of electron. A beam of electron. A pool of electron. Electrons are coming and they are colliding. That's it. It is not light. So, this is not Norris 2. It is only McLaughlin. If I write light symbol here, see if I write photochemical symbol, then that is called Norris 2. But answer is remain same. Advantage of mass spectrometry, no need to learn Norris 2. Same answers. Only thing is, electron beam replaced by electromagnetic radiation. That is called photochemistry. That's why Norris 2 we are learning in photochemistry. Photons we are applying over there. Light energy we are applying. By absorbing light energy, molecule undergo excited. After excitation, they undergo fragmentation. That is called photofragmentation. This is not photofragmentation. That's why if you learn mass spectrometry, advantage is maximum photochemistry questions you can solve very easily. And you can also solve UV spectra easily. Because there is a link between photochemistry and UV. There is a link between UV, photochemistry and mass spectrometry. Because the two are belongs to electromagnetic radiations, but here a beam of electron. Electronic impact, MALDI, matrix, some selective sources will be there to generate a molecular ion. That selective methods you will find in your PG that I will explain. Some selective methods are there where it is responsible to generate a molecular ion. Matrix assisted laser desorption technique is there to generate a molecular ion by using electron beam. Your source is not light, remember. In mass spectrometry, remember, forget about light energy. Only thing is, we are using a beam of electron. Beam of electron means a pool of electrons are coming with high energy. They are contacting the sample. That's it. Okay? So this is called McLaughlin rearrangement. Transfer of gamma hydrogen followed by beta homolysis is called McLaughlin. So that will come later, but right now remember what is homolytic, heterolytic, hemi-heterolytic, then followed by multi-center fragmentation. So that is about types of fissions. Okay. Total 4 types are there. First one is homolytic, second one is heterolytic, third one is what? Hemi-heterolytic, fourth one is multi-center. Multi-center is most important because multi-center you came to know whether that fission is possible or not based on 2 rules, even electron rule, odd electron rule. Some standard name reactions are there in mass spectrometry, especially McLafferty, double McLafferty, O-name rearrangement, okay, then followed by retro-Diels order. These reactions all are belongs to multi-center fragmentation. So don't think that only one center fragmentation, possible multi-center fragmentation also expected in mass spectrometry. Then, so molecular ion is over, then keep heading. Fragmentation. So what is the meaning of fragmentation and how to represent a fragment? Fragmentation. Now 2 points you learn. What is fragmentation? Then how to represent that fragment ion? How to represent corresponding fragment? So what is the meaning of fragmentation? The process of cleaving a molecular ion into small species is called fragmentation. Fragmentation leads to formation of cation, anion or neutral species. But mass spectrometry can identify only what they identify. They will identify only cation. Always fragmentation initiates from molecule or molecular ion. Molecular ion only. Don't make fragmentation from molecule. Okay? Fragmentation is a unimolecular process. Only one molecule, in one particular direction it will take place. So, fragmentation is not a random process. It is a step-by-step successive process. Fragmentation takes place even in the form of a multi-center. Okay, fragmentation follows generally some rules. So fragmentation is always specific. Specifically fragmentation takes place. Randomly not possible. What is the meaning of random? Whatever direction they want. Whichever direction you want, if you break, that is not fragmentation. Wherever you want to break, that is not fragmentation. See, whenever a person is moving on a main road, one vehicle comes and it is hitting that person. Which body part is going to be damaged? Anything is possible or not? That is called random. But it is not random. Fragmentation is not a random process. It will follow one rule. According to the rules, fragmentation takes place. Clear? Right. Ready? Fragmentation. The process of cleaving. The process of cleaving molecular ion into small species is known as fragmentation. The process of cleaving molecular ion into small species is known as fragmentation. Next point. Fragmentation leads to formation of radical, cation, anion, etc. Fragmentation leads to formation of radical, cation, anion, etc. Mass spectrometry usually identifies positive ions. Okay, next. Fragmentation initiates from molecular ion. Fragmentation initiates from molecular ion, but not from molecule. Fragmentation initiates from molecular ion, but not from molecule. Okay, next. It is a unimolecular process. Fragmentation is a unimolecular process. Means one molecule can undergo successive fragmentation. Next point. It is a specific process. It is a specific process, but not random. It is a specific process, but not random. It is a specific process, but not random. You take this. So this is fragmentation. Here you write here we are breaking, not from here. Here key points are random. It is not a random process. It is a, what is one more point? Initiates from molecular ion only. Fragmentation never takes place from molecule. It is not random. It is unimolecular. Only these points are important in this. Next, one more point. It is a successive step-by-step process. It is a successive step-by-step process. It is a successive step-by-step process. So one example I will give. So this is molecule and this is a molecular ion. Now what is the embased value of this molecular ion? You can write embased value only for molecular ion and cation. What is embased value for this? You need to learn 12th table. 1, 2, 3, 4. 4 carbons are present. 48. 48 plus 10. 48 plus 10, 58. Every carbon 12. Every hydrogen 1. How many carbons are present in this molecular ion? 1, 2, 3, 4. 4. 4 carbons are there. 4 into 12. 48. 48 plus 10. 10 hydrogens are there or not? 58. Molecular and embased value. After formation of molecular ion, they undergo fragmentation. Now hemielectrolysis or not? Hemielectrolysis, listen. Here you will get CH2 plus. So what about embased value? What is embased value? 43. 36 plus 5 here. 36 plus 5. 51 plus 41 plus 2, 43. Okay. Then see, this is successive fragmentation. Remove this. If I remove CH3, CH2 plus, and what is removed here? A carbon. Then one more time. Remove this one. Then you will get CH3 plus, and this is CH2 radical. So this is successive fragmentation. Continuously this keep on undergoing fragmentation. Okay. So this cation never takes place from this molecule. This cation formation never takes place from this molecule. They will take place from this molecule only. That is called successive. Step by step process. Doesn't take at a time. See in this one, after formation of molecular ion, what I removed here? CH3 plus or CH3 dot? CH3 dot. But see, what is embased value of this one? Embased value is 29. And what about embased value here? Embased value is 15. So when this molecule undergo fragmentation, you will get a peaks at 58, 43, 29 and 15. 58, 43, 29 and 15. Okay. So the formation of these all ions only from one molecule. That is called unimolecular process. And one more, it is a continuous successive step by step. Step by step means this will form from this. This will form from this. And this will form from this only. This cation never given by this one. Without this formation, it is impossible to get. Right or not? See, this cation never give this one. Suppose if you are getting a peak 15 means it is coming from which one? 29 only. That is called step by step process. Clear? If this molecule placed in mass spectrometry, we are getting this kind of MZ values. But these all MZ values cannot come from all molecules or all fragments. One by one. One by one fragment responsible to give other fragment. Okay? So, 29 never given by 58. 58 never give 29. 59 give, see this, 29 is given by 43. 15 given by 29. Okay? Remember, this 15 never given by 43 as well as 58. So, observe clearly the MZ values. Initially what I used? Initially I use 58. 58 to what we are getting? 43. 43 to 29. 29 to 15. So, what is the difference from molecular ion to fragment? Molecular ion to fragment. Is it molecular ion? Molecular ion to first fragment, if it is a straight chain hydrocarbon, 15. Add 15 to 43. 58. Then from this fragment to fragment how much? 14. Fragment to fragment how much? 14. Successive. Molecular ion, remove 15. Then after removing 15, regularly keep on removing 14, 14, 14, 14. Then based on that we can identify the chain, how much length of chain is present. First 15 difference, later on every time 14, 14, 14. See, add 14 to 15. 15 plus 14, 29. 29 plus 14, 43. 43 don't add 14. 43 add 15. Suddenly if you got 15, means chain is terminated. Suppose see, 15, 14, how much? 29. 29, 14, 43. 43, 14. 43, 14. 57. 57, 14. 71. 71, 15. 71, 15. 86. 86 is a, what is 86? Molecular ion. Suppose if you got 57, is it a molecular ion? Here if I get 57, no. Then what is that? One of the fragment ion. This 43 comes from 58, 29 comes from 43, 15 comes from 29. Successively, step by step. If it is a continuous process, means chain length is very high. That is the meaning of fragmentation. Fragmentation means continuously we are breaking into small pieces. Suppose see one big stick we are taking. This is a big stick. Okay, I want to make them into small pieces. I want to break like this, small pieces. Can you break this into small pieces with one time? By hitting one time? If you hit one time, can you get small pieces? A stick we are doing, a wooden stick we are taking. Is it possible to get small pieces? No. Means we need to make multiple times hitting. So multiple times if we use, you will get a small pieces. That small pieces nothing but fragments. Here also same. So this is representation, how to represent a fragment ion. Representation of fragment ion. What we learned just now? What is fragmentation? What is fragmentation? What is fragmentation? Breaking a molecular ion into small species. Is it a random process? No, it is not a random process. It will follow one rule. Okay? Every time one fragment responsible for one species only. All fragments cannot form at a time from molecular ion. That is a key point right now. Right now, one point you need to keep in your mind. That is, fragmentation cannot take place from molecular ion at a time. See, can you prepare CH3 plus directly? No. Is it giving molecular ion? Is it CH3 given by molecular ion? Yes, molecular ion is giving, but not directly. CH3 is given by molecular ion, not directly. First it is giving this one, then it is giving this one, then it is giving this one. You remember this. Is this molecule responsible to give CH3 plus or not? Yes, but not directly. It can give C15, M by Z 15 fragment, but not directly. Indirectly it will give. Right or not? See, your grandfather is there, and your father is there, and you. You are source of your father. Your father is source of your grandfather. Right or not? It is a step-by-step process or not? Like that, generation, one generation to other generation. First generation to fourth generation possible directly? Impossible. First generation to fourth generation not possible. Without second generation, without third, this is your grandfather. This is your father. This is yourself, and this is your children. So your grandfather to your children possible? That generation possible? No, impossible. But you will say that these children and this grandfather, one link is there. What is that link? So this person initially initiated by father, grandfather, like that. Okay, here also same. So especially your surname. Do you know your surname history? Surname. Every person having one surname is there. Do you know the history of that surname? That is a step-by-step process. It will come from your parent, father. If you ask your father about your surname, if father say, I don't know, I am following my father. He will follow their father. So means a big history is there. So it is coming from grandfather. Okay, so that is called fragmentation. Now how to represent a fragment ion? Fragment ion is represented by, see this is called molecular ion minus mass of fragment. Mass of fragment loss. You enclose in box. It is first way of representing. M is what? Molecular ion. Molecular ion minus mass of fragment loss from molecular ion. Okay? Then we can also write M minus formula of fragment lost. Formula of fragment lost. Which one is lost? That we need to write. And one more way of representing directly by M by Z value. This is three ways of representing a fragment ion. How to represent a fragment ion? Three ways we can represent a fragment ion. What are they? Molecular ion minus mass of fragment loss. From molecular ion, what we are removing? Okay? Suppose this is a fragment. In this, what I removed? In this, what I removed to get this one? CH2. This is CH2 or not? This I removed from this to get this one. This you can represent by directly M by Z. This is most commonly we will use M by Z. But three ways we can write. Sometimes they will write directly molecular ion minus mass of fragment ion. Molecular ion minus formula of fragment ion lost. I will show one example. These are the three ways you can represent anyone. But better you practice M by Z only. First you complete this. Don't write, just listen. First you listen, then you write. You first complete this. How many carbons are present? 5 carbons or not? 5 carbons. So 5 carbons, then what is this? This is molecular ion. Molecular ion we can also represent it as M. This is molecular or not? It is M. Don't think it is molecular ion. While writing in this form, M. What is the formula of molecular ion right now? Molecular formula. How many carbons are there? C5, 1, 2, 3, 4, 5. How many hydrogens? 12 or not? C5H12. Is it radical cation? C5H12 radical cation. So this M indicates this one. Clear? So in this one I am removing one fragment here. What is this? Hemielectrolysis or heterolysis? Hemielectrolysis. If I remove this one, what about MZ value? CH3, CH2 and here one more CH2 plus. Then what is MZ value of molecular ion? Molecular ion MZ value. 72. 1, 2, 3, 4, 5. 5 into 12, 60. 60 plus 12, 72. Here MZ value is 72. Right? This is a fragment ion of this parent or not? Okay. So now see, from original molecule, what I removed? How much mass I removed? 15 or not? M minus 15. Like that we should write. M minus 15. Or else one more. What is one more way? What is the mass of fragment lost? Formula of fragment loss. Is it CH3 is removed or not? Then what is one more? M by Z value. What is M by Z value of this fragment? 57. This fragment M by Z value I am saying. This is comes from parent. From parent what I removed? M minus 15. Mass. This 15 I removed. CH3 15. CH3 formula. So from here I can write one more fragmentation. Heterolysis. What you will get? CH3 CH2 and this is CH2 plus or not. Now see, this is molecular ion. From molecular ion, which fragment if I remove you will get this one. From molecular ion. From molecular ion, which group if I remove to get this one? What is M indicates? Molecular ion. From molecular ion, I want to remove one group. If I remove that group, then only you will get this one. What is that group? M minus. Which one should I remove? C2H5. How it is possible? From molecular ion, if I remove C2H5, then only you will get this one. What is M here? Molecular ion. In molecular ion, if I remove C2H5, you will get this one. Don't try M minus CH2. M minus CH2. Indirectly you are saying that M means this one on the time. Okay. So you can write like this. Then one more way. M minus, can I write 29? 29 is removed or not? Then otherwise you write one more. What about M by Z value? M by Z value is 43. Is it clear? Now, can I take one more example? See, if I remove this one, so what will get? CH3, CH2 plus or not? Now, from molecular ion, what should I remove? See, from molecular ion, if I remove some group, I will get this one. What group should I remove? C3H7, very good. C3H7. If I remove C3H7, then only you will get this one. Okay, what is the mass of C3H7? M minus C3H7 mass. How much? 43 or not? Why you are hesitating? This one only. 43 I removed. Then what about M by Z value of this fragment? This fragment M by Z value, 29. This one is 29. Okay. Suppose if I remove one more CH2, I will get CH3 plus. Then how to write? M minus M minus. From molecular ion I got CH3. So this part is removed or not? How many carbons, how many hydrogens are removed? C4H9. This is C4H9. Then what about mass of C4H9? M minus 57. Then what about M by Z value? How to write M by Z value? You can write M by Z value for CH3. Directly it is 15. M by Z value means only for this one. M minus this number indicates that it is coming from parent. From parent value you need to write every time. Are you able to understand, or can I explain one more time? Clear? Right. So you better practice with M by Z only. This is a little bit confused, but this is also important one for you. Means, see, this is molecular ion. Molecular ion nothing but M. From molecular ion, I got this one. Means what I removed? CH3 I removed, 15 mass. And here also, this is obtained from this one. Okay, that is okay. But without molecular ion, is it possible? No. Directly this can't be generated. But indirectly comes from this one. But if you compare the formula with molecular ion and this fragment, how much difference? That you need to write. From molecule, if I remove C2H5, you will get this one. This C2H5 mass is 29. Then this M by Z value is 43. Clear? Right. Which is easy, M by Z or M minus formula, M minus last mass? M by Z only. M by Z indicates that, see, this M by Z, here also written M by Z, here also given M by Z. This M by Z only for this cation. This value I represent only for this one. But here this is molecular ion. From molecular ion, if I remove 15, you will get this. From molecular ion, if I remove CH3, you will get this. That is the meaning. Who is molecular ion here? M. M is not this one. Remember, if you represent any fragment by using these closed brackets with M, this M indicates this one only. Clear? Can I give one more? Will you work out? So now we are representing a fragment ion. How to write a fragment ion? Okay. So I am giving a benzene. You need to work out this. When benzene on electronic impact, there is a formation of molecular ion. This is radical cation like this. So this is M or not? Is it M? Then what is the formula? What is M formula? Molecular formula I am asking. How many? This is molecular formula. How many carbons and how many hydrogens? C5H12. What is the molecular formula here? C6H6. This is molecular ion. Clear? Now, molecular ion responsible to give one fragment ion like this. See, I am breaking homolytically, and what you will get here? Radical. This radical forms one double bond or not? Double bond, and what is this? Plus. What I removed? In this molecule, what I removed? Hydrogen. Then how to write here? M minus what should I write? From molecular ion, I removed some group or atom to get this one. Which group I removed? Which atom I removed? Hydrogen. So M minus H. One more way. How to write? M minus 1. What is the mass of hydrogen? 1. Then what is MZ value of this cation? MZ value. What is molecular and MZ value? 78 or not? 78 or 58? 78. Then what about this one? I removed one hydrogen or not? 78 minus 1, 77. Okay. Then see, one more fragmentation I am showing now. See, this is multi-center fragmentation. If I break this and if I break this, then what happens? So this radical forms, this and this forms single bond, and here double bond, and here C, positive. What I removed? Carbon, triple bond or not? Can I remove carbon, triple bond like this or not? Yes. Now see, the question is, how to represent this fragment? How to represent this fragment? M minus. M is molecular ion. From molecular ion, I would like to remove one group to get this one. Which group should I remove? C2. What is M here? What is M? Molecular ion. Means you are saying that from C6H6, if I remove C2H4, you will get this one. Right? No. What is the molecule formula here? C6H6. C. From C6H6, if I remove C2H2, then what is your answer? This is C4H4 or not? Means you are saying this molecular formula C4H4? Say, here how many hydrogens are there? How many hydrogens? 1. Here, 1. Here, 1. And what about this carbon? No hydrogen. See, if you add this and this, see, C2H2, if you remove from this, you will get C4H4. Right? C4H4. Is this is a C4H4? No, that is not C4H4. Already one hydrogen I removed. Here one hydrogen I removed or not? Where that hydrogen goes? So I can write C2H3. This hydrogen and this fragment, both you need to add. C2H3. If I add this C2H3 here, from molecule if I remove C2H3, then you will get this one. What is the molecular formula? This formula. C6H6. In this I removed one hydrogen or not? I removed hydrogen here in the form of radical. Then what is this formula? C6H5. It is not C6H6. Here already one hydrogen I removed or not? From where I removed hydrogen? C6H6. This is C6H5. From C6H5 I removed C2H2. Now this M is not this one. M is this one. Then what is M? C6H6. From C6H6, if I remove C2H2, you will get this one? No. C2H3 we need to remove. Okay? So, one more possibility, M minus. What is the mass of this one? Two carbons, 12 plus 12, 24. 24 plus 3, 27. You need to practice the 12th table. Then what about MZ value of this one? You need to count carbons and hydrogens. How many carbons, how many hydrogens are present? 4 carbons, 3 hydrogens. 4 into 12, 48. 48 plus 3, 51. This is MZ value. Remember, this is common for benzene. When benzene is present, remove. When benzene is present, remove hydrogen first. Then remove triple bond. Then every time when benzene is present, 78, 77, 51. These three are common peaks. 77, whenever if you are getting, 51 is 100% you will get. 77, 51 you remember every time. Clear? So what is the formula of this one? C6H6. What is the formula of this one? See, from molecule if I remove one hydrogen, then what is the formula? C6H5. From molecule if I remove C2H5. From molecule. What is the molecule? From molecule if I remove one hydrogen, I got C6H5. From C6H5, if I remove this one, you will get this one. Otherwise, from benzene, if I remove C2H3 from benzene, means from C6H6, if I remove C2H3, then what happens? C4H3 or not? What is this formula? C4H3. What about C4? C4 means how many carbons? 4. 4 into 12. 48. 48 plus 3. You can check like that. Generally, while writing this two, you will think this one. Wrong. You compare with the original molecule. While writing M-based value, compare direct molecule. If you understand really, you work out this example. This is lone pair, 70 electron volts. I prepared a molecular ion, phenol. What is MZ value of phenol? What is the molecular formula? MZ value of phenol. Every oxygen 16, every nitrogen 12. 90? Count clearly. 94 is right. +78 +16. This is original molecule in the form of molecular ion. What is the formula? What is the molecular formula? C6 C6H6 or not? C6H6O. Is it phenol? 1, 2, 3, 4, 5, 6. 6 carbons. 1, 2, 3, 4, 5, 6 hydrogens. 1 oxygen. Right? In this C, I am removing hydroxy. Heterolytic fission. Heterolytically if I remove, I got phenyl cation. Now, M minus, what should I write? From original molecule, which group should I remove to get this one? OH. Can I write OH here? This is OH. Then we can also write one more way. What is that? M minus. What is the weight of OH? Mass of OH. Every 16, every oxygen 16. 16 plus 1, 17. Then what about MZ value? MZ value of this one. Already given just now. Benzene MZ value. 77. This one only, 77. Now in this one I would like to remove one triple bond. If I remove triple bond, I will get this one. See, this is plus, and what should I remove? Carbon, carbon, triple bond like this. Now the question is, M minus C. From original molecule, which group should I remove for getting that one? From this molecule, which group should I remove for get this one? C2? Try. C2, H2 or 3? H3? Oxygen or not? You add this fragment and this fragment, you will get the answer. From this molecule, if I remove OH and if I remove C2H2, you will get this one. So what is the mass of this particular fragment? M minus. Every carbon 12, every oxygen 16, every hydrogen 1. 40? Very good. 43. It is M minus 43. Then what about MZ value of the given fragment? Just now given. 51 or not? What is MZ value of this one? So wherever you are getting 77, definitely one peak is appeared. What is that peak? 51. So in mass spectrum, mass peaks are represented by MZ value only. You should be familiar with MZ. But sometimes in examination, logically they are asking like this, whether you have this practice or not. If they given directly MZ value, you are safe side. No problem at all. But if they ask this data, so they will give one molecule. A molecule with a molecular formula C6H4, like this they will give. Later it will undergo fragmentation by removing this group. They will give like this. C3H3O is a group which is removed from the molecular end by liberating MZ value 51. Like that they will give some data. Theoretical questions. On that time if you know this pattern to identify the fragment, it becomes very easy for you. Clear? Right.
So that is a representation of a fragment. Clear? So two major concepts we learn today, especially for fragments. How to make fragmentation, how to represent a fragment ion. And initially we learn what are the types of fissions they have. Homolytic, heterolytic, hemi, heterolysis. Later on, what is fragmentation, what are the steps required for fragmentation, how to represent a fragment. So next concept is types of ions. Next is types of ion, that I will explain in your next class. So there you will see what is molecular ion, fragment ion, how to represent in mass spectrometry. Then what is even electron ion, what is odd electron ion. Then multiply charged ion, metastable ion. Okay. Then we can also go for molecule, molecular ion, interaction, ion. Then isotopic ion, negative charged ion. Negative charged ion is also there, but we can't identify by using mass spectrometry. Okay, so that is about today's class. So see you in your next class. We'll stop here. We'll continue your next class. Okay, so tomorrow we are declaring holiday. There is no classes tomorrow. So next class will be after your Sankranti holidays. Sunday to Sunday we are declaring holiday. Offline classes are not available. No offline classes. No need to come here, especially for offline students I'm saying. Most probably we are planning to take a online class, online mode. This class will be continued in online mode. After this, next, what is the topic? Types of ions. That I will explain directly in online. In class 1 I will explain, but you people are not allowed to come because we are declaring holiday from Sunday to Sunday. But I will take online class that you can directly listen that live class. Otherwise, you can also listen that recording class by watching in WhatsApp group. So whatever classes are going on right now, that all classes we are giving in recording form. Directly we are providing in your WhatsApp group only. Still we are not added any kind of video in your app. Okay, so no need to search in your app, just see the videos in your WhatsApp group only. Later we will add this all videos in your app itself. Okay, but you remember follow the sequence. Mass spectrometry 1, 2, 3, 4. If you follow the sequence, then only it is easy to understand. Okay, so mostly this from tomorrow to up to Sunday there is no offline classes. Only online classes will be there, and that too we are going to inform that online class timings in your WhatsApp group. Even if you miss that class, nothing to worry. Okay, that video will be provided in the form of recording video. Because even for live class also, you people are not allowed to ask any question. Even for recording video also, it looks same. So that's why we are not conducting any kind of offline classes from Sunday to Sunday. Next offline class will be on Monday, next Monday. Means on 19th. On 19th, offline class will be there. So see you on that day. Okay, we'll stop here.